We have the privilege of beginning with Raymond Kurzweil, who I'm sure all of you are aware of, and if you're not aware of him, you certainly have felt the impact of his innovation in all sorts of technological areas, from character recognition to voice recognition to speech synthesis. His literal title is the CEO of Kurzweil AI, but also is it crucial to know that he's a recipient of the National Medal of Technology, a member of the Inventor Hall of Fame, the recipient of 13 honorary doctorates and of awards from 3 U.S. presidents. Everyone here should have received, in addition to other books by our conference participants, Mr. Kurzweil's book, The Singularity is Near, which significantly is #1 in both the science and the philosophy sections of Amazon.com. Please join me in welcoming Raymond Kurzweil.
Well, it's a pleasure to be back here on the campus. I was here 3 weeks ago and had the opportunity to share ideas with the Google staff, which was stimulating, about my new book. And I'd like to share with you ideas I have that I've been developing over 30 years on 3 important trends. The exponential growth of information technology, which is not just computers, it's not just telecommunications. The second major trend is that information technology is increasingly pervasive, affecting everything we're doing. We're understanding our biology as information processes and gaining the tools to reprogram them. I mean, how much software do you use that you haven't changed in 30 months, let alone 30,000 years? And that's about the amount of time in which we haven't changed our genetic information. And there's some genes we'd like to turn off. I'll come back to that. And the third is the increasing decentralization of our technology base, of our infrastructure, which is really being facilitated by this exponential growth of the power, price, performance, bandwidth of information technology. The long tail is a good example of that. We've democratized the means of creativity. A college student in her dorm can command the equivalent of a $1 million studio of 20 years ago. The same for making movies. A blogger with a PC can reach millions of people. We will ultimately actually democratize the means of production once we get to full-scale, tabletop molecular nanoassembly, which I believe we'll see within about 20 years. So we'll be able to actually fabricate just about anything we need from inexpensive information resources. So let me take you quickly through this, and I think this is a good audience to try to compress this into 20 minutes. But things have been accelerating. This actually goes back to biological evolution. But in technology, it took half a century for the first virtual reality technology, the telephone, where you could actually be with someone else, despite being hundreds of miles apart. That never happened before a century ago, but that took half a century to be adopted by a mass audience, by a quarter of the U.S. population. Recent technologies like the PC, cell phones, the web were adopted in about 8 years' time. I mean, blogs, it's like 2 or 3 years. And if you look at different information technologies, telephone, radio, television, took decades to be adopted. These recent technologies are measured more in a few years' time. And I don't want to dwell on this slide, but there's been a basic acceleration. These are powers of 10 on the x-axis to how long ago this paradigm shift took place, and on the y-axis, how long it took to implement that paradigm shift. So the first paradigm shift, which was actually creating an information backbone to evolution itself, to biology, DNA, actually RNA came first, took billions of years. But evolution works through indirection. It creates a capability and then uses that capability to bring on the next stage. That's why an evolutionary process accelerates. And we can simulate evolution in the computer with genetic algorithms, something I've done in the field of pattern recognition for several decades. And we see the same type of acceleration. So the Cambrian explosion, where all the body plans were evolved, went 100 times faster. Only took about 10 million years. And biological evolution kept accelerating. Homo sapiens evolved in a few 100,000 years. Only actually 3 minor genetic changes involving a few tens of thousands of bytes of information distinguish us from our as yet unidentified primate ancestor. A larger skull at the expense of a weaker jaw, so don't get into a biting competition with another primate. More of our brain is devoted to the cerebral cortex, and we have an opposable appendage that works. Chimpanzee, the pivot point is down by an inch, so they don't have a power grip, they don't have fine motor coordination. We can actually manipulate the environment, and that brought on the next evolutionary process, which was technology. The first stages were a little bit faster, stone tools, fire, the wheel, were tens of thousands of years, and then we always used the latest generation to create the next. So half a century ago, the first computers were designed pen on paper, and now we, of course, use computers, and computer-assisted design software will work out 10 different layers of intermediate design. And you can see that this is a straight line showing this continual acceleration on this powers of 10 logarithmic graph. If you look at it on a linear graph, it looks like everything has just happened. But some people said, well, Kurzweil only put points on this chart that fit on the straight line. So I took 14 different lists, Encyclopedia Britannica, American Museum of Natural History, and Carl Sagan's Cosmic Calendar. And they have different lists and different ideas of when things happen, but you can see the same basic trend line. But the basic power of information technology is doubling every year. And that's pretty phenomenal. It's a 1,000-fold increase in 10 years, 1 million in 20 years, 1 billion in 30 years. There's actually a slow second level of exponential growth, because when we put more resources into a certain type of capability, the industry grows, the research grows, and it actually accelerates the rate of acceleration. So we'll see a 1 billion-fold increase in the power of information technology in 25 years, and it's already deeply influential. So a factor of 1 billion is going to make a very substantial change to human society. Personal experience, computer took about half the size of this room, quarter of a MIP, 144,000 bytes of memory, $11 million in cost, much less powerful than the computer in your cell phone today. But Moore's law is just really one example of many within computation, and also computation is just one example of this sort of exponential growth of price performance, bandwidth, and capacity of information technology. This is 5 different paradigms through a century: the 1890 data processing equipment that was used in the 1890 census, then Alan Turing's relay-based computer that cracked the German Enigma code, CBS's vacuum tube computer that predicted the election of Eisenhower in 1952, first time that we did that, the discrete transistor computers used in the first NASA space flights, and then several decades of Moore's law, integrated circuits, shrinking transistors on an integrated circuit. And you see smooth exponential growth through that whole progression. In the 50s, they were shrinking vacuum tubes, making them smaller and smaller to keep this exponential growth going. That paradigm hit a wall. But that was not the end of the exponential growth of computing. Another paradigm came. And we'll hit a wall with Moore's law. The first predictions were 2002. Intel now says 2022. There's actually a published roadmap by the semiconductor industry that foresees 5 nanometer features by 2018. That's only 25 carbon atoms. They'll come to a point where we can't shrink them anymore. That'll be the end of Moore's law. But that won't be the end of this exponential growth of computing. We'll go on to the 6th paradigm, which is computing in 3 dimensions. Chips are very dense today. They're already nanotechnology. They're under 100 nanometers, 65 nanometers per features, but they're flat. We live in a 3-dimensional world. We might as well use the 3rd dimension. There's already been tremendous progress, for example, with carbon nanotubes. There's a carbon nanotube-based memory being introduced next year. We'll have 3-dimensional molecular circuits working well before we need them to keep this exponential growth going. And supercomputers will hit the processing power required to emulate the human brain early in the next decade. And I don't really want to dwell too much on these different examples, but I mean, look how smooth this graph is. You could buy 1 transistor for $1 in 1968. You could buy 10 million in 2002. It's about 100 million today. I mean, this looks like the output of some tabletop experiment. It's a very smooth progression. Yet this is the result of millions of people, hundreds of companies, dozens of countries, with all kinds of chaotic activities and recessions and IPOs and bankruptcies, very smooth exponential growth, which brings up an issue: can we predict the future? Well, the common wisdom is you can't, and lots of speakers will eagerly recite lots of bad examples of predictions from times past. And it turns out it's very hard to predict individual projects. What will the next wireless standard be, for example? But the overall price performance, capacity, bandwidth of these information technologies is remarkably predictable. And we see other examples in science of being able to have a predictable result out of a lot of chaotic activity at the micro level. Predicting the movement of one molecule in the air is essentially impossible, yet the overall properties of a gas, consisting of many randomly, chaotically interacting particles is very predictable according to the laws of thermodynamics. And technological evolution is similarly a very complex, chaotic system where the overall fruits of it, the price performance of these technologies, follows very smooth, predictable curves. And I say this now not just looking backwards at an overfitting to past data. I've been making these forward-looking predictions for 25 years based on these kinds of models. As we make the transistors smaller, they're faster, so we have exponential growth in the speed. So the cost of a cycle, transistor cycle, which is a true measure of price performance, has been coming down by half every 1.1 year. If you add in some other levels of innovation like pipelining and data caching, we're doubling the price performance of electronics every year. And it turns out it's true of every other form of information technology. Genetic sequencing, the cost of sequencing a base pair of DNA has been coming down by half every year. Telecommunications, the cost of moving a bit around wired, wireless, comes down by half every year. Pervasive 50% deflation. And we actually more than keep up with this deflation. Economists say, well, if you have this deflation, people aren't going to actually buy twice as much stuff. They actually do better than that. We've had 18% compounded growth for the last 50 years in every form of information technology. It's already a substantial portion of the economy. It will be a majority of the economy by the 2020s. Magnetic data storage, I just put this up because it's a different technology, different engineers, shrinking magnetic spots on a substrate, same exponential growth. And I mentioned this biotechnology revolution. We've gone from $10 per base pair in 1990 to about a penny today. And there's many other examples. As we're understanding the proteome, for example, we see the same type of exponential growth. The Genome Project actually was controversial when it was introduced in 1990. Mainstream scientists said, there's no way you're going to do this. We just sequenced 1/10,000th of the genome in 1989. It'll speed up some, but there's no way you're going to do the whole thing in 15 years. And 10 years later, the skeptics were still going strong, saying, I told you this wasn't going to work. I mean, here we are 10 years to a 15-year project, and you finished 2% of the project. But it's the last 7 doublings that go from 1% to 100%, and the project was done on time, and we've continued this exponential growth. This is a logarithmic graph, and that represents doubling every year the amount of genetic data that we've sequenced. And regaining the tools, as I mentioned, to reprogram our biology. We can actually change our genes now. We're at the very early stages. RNA interference, it's a new technology, just emerged a couple of years ago, allows us to turn genes off. We send in messenger RNA, it latches onto the messenger RNA in the cell, expressing that gene and destroys it, and effectively turns the gene off. When we turned off the fat insulin receptor gene in mice, that's a gene that says hold on to every calorie because the next hunting season may not work out so well. These mice ate ravenously and they remained slim, and they got the health benefits of being slim, including the health benefits of caloric restriction. Despite doing the opposite, they lived 20% longer, and there are 5 pharmaceutical companies rushing to bring fat insulin receptor inhibitors to the human market. And there's a lot of other genes we'd like to turn off that are required for heart disease or cancer to progress. And that's only one side of the reprogramming. There's new techniques for doing gene therapy to actually insert new genetic information. I'm involved with one company that has a new technique that's actually worked in animals for curing a fatal disease, pulmonary hypertension, that reliably places the genetic information on the right chromosome in the right place, and it's going into human trials. And there's many other examples of that. We can turn on and off enzymes, which are the workhorses of biology. So Pfizer's torcetrapib actually destroys a specific enzyme that's needed in a certain stage of atherosclerosis for it to progress. The phase 2 trials, it was effective in halting atherosclerosis. It's now Pfizer's spending a record $1 billion on the phase 3 trials. And that's just one of thousands of examples of this rational drug design, which contrasts with how we used to do drug development, called drug development, where we just find something that happened to work with no real theory as to why it works. We're now actually understanding and gaining the tools to reprogram these information processes. And it's an exponential process. 10 to 15 years from now, this technology will be thousands of times more capable than it is today. We'll have very powerful tools to really turn off cancer, heart disease, and even the processes underlying aging. Communications, another dramatic technology. We talked a lot about that this morning. Many different ways to measure that. I saw a little bit of this graph in the 1980s when I wrote my first book, The Age of Intelligent Machines. Saw the ARPANET doubling in size every year, but nobody noticed it when it went from 10,000 nodes to 20,000 to 40,000, serving a few thousand scientists. But it was clear to me that that would continue, and it would be 10 million, going to 20 million to 40 million to 80 million in the mid-1990s. If we look at this on a linear graph, it looks like the internet came out of nowhere in the mid-1990s, because this is how we experience technology. We live in a linear domain. It seemed to come out of nowhere, but if you looked at the logarithmic trend, the exponential trend, you could see it coming. Another exponential trend is miniaturization. We're shrinking technology at an exponential rate. There's actually many examples, which I talk about in my book, of being able to actually build molecular devices now. That one robot actually built a little robot that walks with a human-like gait, built at the molecular level. We're showing that we can actually manipulate molecules and atoms and molecular fragments and build useful devices. You're watching an animation of a design of a robotic red blood cell that if you replace 10% of your biological red blood cells with this device, you could do an Olympic sprint for 15 minutes without taking a breath, or sit at the bottom of your pool for 4 hours. And if nanobots or blood cell-sized devices in the bloodstream sounds very futuristic and far out, I would point out there's 4 major conferences reporting on these types of experiments, which we're already doing in animals. One scientist actually, with a nano-engineered blood cell-sized device, 7 nanometer pores, cured type 1 diabetes in rats, and they're now gearing up for human trials. If you factor in these exponential trends, I mean, a factor of 1 billion increase in computation and communication, a shrinking of over 100 per 3D volume in the size of mechanical technology every decade, and factor that into what we can already do today, these nanobots will be quite sophisticated in the 2020s. They'll be able to go inside our bodies and keep us healthy from inside. This is the same exponential growth of computing I showed you before. It will cross over to a human brain by 2020. That's the hardware side of the equation. I think that's actually relatively uncontroversial today, although it was controversial when my last book came out 7 years ago. But the more controversial issue is, can we understand the software of human intelligence, the methods? Otherwise, we'll just have very fast calculators. And I would point out that narrow AI already permeates our modern infrastructure. Would really stop functioning if all the artificial narrow AI programs stopped working. But ultimately, we will learn a lot about how human intelligence works by reverse engineering the human brain. And here again, not surprisingly, we see exponential growth in the spatial resolution of brain scanning. Actually doubles every year. The amount of data we're getting is doubling every year. But then the issue is, can we understand this data? Or, I mean, Doug Hofstadter has said for years that maybe our intelligence is just below that threshold needed to understand our own intelligence. And if we were smarter and able to understand it, well, then our brain would necessarily be that much more complicated and we'd never catch up with it. But that is, in fact, not what we're seeing. There are several hundred regions of the brain. There are many parallels between the regions, but they have different functions. And we're actually showing that we can understand them and actually build models and simulations of the regions for which we already have data. This is a block diagram of 15 regions of the auditory cortex, which have been modeled and simulated in software. And applying sophisticated psychoacoustic tests to the simulation gets very similar results to the same tests applied to human perception. Similarly with the cerebellum, which comprises more than half the neurons in the brain, we have a very effective simulation. It's a complex issue, but I talk about it in detail in Chapter 4 of the book that you received. And I think it's a conservative estimate that we will understand human intelligence and really have detailed models and simulations of all several hundred regions by the late 2020s. All of this is driving economic growth. E-commerce, I put this up because it's particularly relevant here. You might say, well, where's that boom and that bust? That was strictly a Wall Street phenomena, which actually accurately is a harbinger of true revolutions. But the actual adoption of e-commerce was smooth exponential growth through boom and bust. I mean, it was only a few years ago that people said you can't make money in internet advertising, and clearly that perception has changed, particularly on this campus. Information technology, even narrowly defined, will be a majority of the economy by the 2020s. And I'll just end, since I'm about out of time, with a few scenarios. Computation will really decentralize into a massive number of nodes. These nodes will not just be spokes into the internet, they will be receiving and transmitting nodes, sending other people's messages. There'll be a very seamless, very decentralized web of computing and communications early in the next decade. Images will be written to our retinas from our eyeglasses and lenses. I've tried out these devices, which the Army uses since I'm on their advisory board. They're expensive today, but they're actually quite effective. They'll be inexpensive. In the future, we'll be able to enter virtual reality environments. We'll have interaction with virtual personalities as a primary interface, effective language translation. And if we go out to 2029, we'll have, as I mentioned, a factor of 1 billion increase in these technologies. We'll understand how human intelligence works. We'll be able to apply these very powerful models to computers at that time. $1,000 of computation will be 1,000 times more powerful than the human brain. So these devices will combine the subtleties and suppleness of human pattern recognition with ways in which human intelligence, with ways in which computers are already superior to us. I mean, this can remember billions of things accurately. It can share its knowledge at electronic speeds, which is 1 million times faster than human language. But it's not an alien invasion of machines come from over the horizon to compete with us. It's emerging from within our civilization. We already routinely do feats that would be impossible without our machines. We're moving closer to our technology. It's in our pockets. In the next decade, it'll be in our clothing and the environment. It'll ultimately be in our bodies and brains, extending human intelligence. And if you want to live to see that, this next trend is interesting. Human life expectancy was only in the 20s thousands of years ago. It was not in the interest of the human species for people to live much past child rearing. It was 37 in 1800. Antibiotics and sanitation has brought it close to 80. This full mastery of the biotechnology revolution will extend it dramatically further. So if you can take care of yourself the old-fashioned way for another decade or so, we may get to experience the remarkable century ahead. Thank you very much.
Thank you very much to Ray Kurzweil for a phenomenal 20-minute distillation of what's in his fascinating book, which again is available to all of you. When hearing about the Hofstadter paradox, that if we were smart enough to understand our own brains, our brains would be too big for us to understand, I was reminded, of course, of the country song, which could be a motto for this, "I'm my own grandpa," but we can go into that later on.